Are we connected? I'm not sure. So then we lost.
Yes, we are connected. So, hello everyone. Welcome to the JLR's Powered Bonnet for Electrical Vehicle event. So, I want to introduce about the panel today. We have with us Mr. Ankit, Mr. Dipanshu, Mr. Alok, Mr. Vatsal, and Mr. Abhishek from JLR. And now we will be having the presentation for which I will give a brief introduction and instruction. So during the entire presentation, there should be no name of your IIT disclosed. Otherwise, you will be penalized 5% for this. All the presenters of each team are expected to raise their hand on the platform before their turn to receive an invite from the host to present live on this stage. And only a maximum of two participants per team will be allowed to present. That is, they will be given the speaker and presenter rights, and all the five participants can take up the Q&A session. And each presentation will be of 10 minutes long, followed by a 5 minutes Q&A. So just follow this 10 minutes strict deadline. There will be a buzzer before 2 minutes completion of your entire presentation, and if you exceed this 10 minutes, then you will be penalized for this. And now I would like to call Vatsal. He want to just brief on some PS from his side. Okay, Vatsal.
Okay, am I audible, guys?
Yes.
Yes, you are audible.
Okay, so thanks a lot, everyone, for joining. Thanks a lot, everyone from JLR, as well as all the participants for participating in the event. So the brief overview the of the problem statement, all of you guys already know. Just make sure that you stick to the basics, and we will have a so you already know about this, that we will have a presentation. Just cover all the points, and finally we will go for a Q&A session, so it should run smoothly. And yeah, okay, all the best, guys. Let's make a good like we will also learn a lot of things from this. So yeah, let's try to have a great event and have fun. Thank you, everyone.
Okay, so first team that will be presenting is team ID 8. You can raise your hand. I will give you the presenter access. And even the members who will be answering, they have to also raise the hand. Okay, I have given you the access. Are you able to present the screen?
Wait, let me check. Is my screen visible?
Yes, your screen is visible. Okay, so you can start your presentation.
Yeah. Am I audible?
Yes, you
Yes.
are audible.
So good afternoon, judges and everyone else present in this meeting. I, Gautam Shetty, along with one of my teammates, Aditya Sharma from Team 8, will be delivering our presentation today. Next slide. Before beginning our design process, we first researched powered mechanisms that are already available in the automotive industry. Our tailgate systems present in the market contain a push rod with pneumatics or hydraulics, tension or gas springs as actuation mechanism. After careful analysis, we found that a linear actuator with electronic feedback would be a viable component for the design we are going for. One of the mechanisms that we ideated was employing a simple slider crank mechanism coupled with a linear actuator on each side of the bonnet. Upon the retraction of the linear actuators, the slider moves inwards and the crank moves up, causing the bonnet to lift. This mechanism was rejected due to the more significant number of components, resulting in multiple joining points, hence greater losses of energy. This would affect the efficiency of the whole system drastically. This mechanism comprises a linear actuator whose one end is mounted on the chassis under the bonnet, and the other is mounted on the bonnet itself. The extraction of the linear actuator results in the bonnet pivoting around the chassis mount and lifting the bonnet upwards. The mechanism was selected as it consists of the least possible moving parts with which the said actuation of the bonnet can be attained. Less number of components also implies better packaging and weight reduction. Moreover, the easy availability of the necessary parts in the Indian market further strengthened our conviction to move ahead with this design. The Cytron motor controller is placed on the left side, along with the Arduino, which will run the control algorithms. The Cytron controller will take power from the battery of the car and provide the appropriate PWM signal to the actuators. The IR sensors are also connected to the Arduino, which will sense the gestures and take the appropriate actions. The powered bonnet can incorporate a gesture-based sensor, which allows automatic opening or closing of the powered bonnet by kick motion. Further, a safety feature can also be included, which stops the closing of the bonnet to prevent injury in case of accidental obstruction. These features would ensure ease of access and safety for the user. In the closed position, we fit the whole mechanism assembly in 32.37% of the total available space. This again was made possible because a mechanism with least possible moving parts was used. Going over to the governing equations, here we have derived the mathematical equations necessary to model the physics of our mechanism using the parameters that are available to us. A free body diagram in motion was created to obtain the necessary force balance relations. The Simling model on the right embodies the final differential equation attained in terms of the variables, that is, the actuator force and bonnet angle. Another model was created to convert the input length variable from the electrical subsystem into the bonnet angle. The equation for that was derived through the geometry of the mechanism. Now we will look at the MATLAB scripts that we have developed. The equation mentioned in the previous section is solved here using the F0 solver present in MATLAB. The equation is solved numerically and the solution is usually obtained instantly. The bottom script is the master file, which contains all the necessary constants which describe our problem. The parameters here can be changed to obtain simulation results for a variety of different loading, mass, or time conditions. Now over to Aditya Sharma.
After developing the mathematical models, we went on to select the appropriate linear actuator for our design. Since each linear actuator had different specifications, detailed simulation was done on each model to check if it was able to meet the requirements. After several iterations, we found that TA23 linear actuator was able to provide the desired force and speed with enough leeway for further adjustments. On contact with the seller, we found that TA23 was currently TA1 was currently unavailable, but fortunately they had TA23 model which was exactly same spec. So we finalized the TA23 linear actuator for a further design. After selecting a linear actuator, we have to decide the exact position to mount it within the given space to us. For this, a 2D SolidWorks sketch was created to identify the optimal point. Two semicircles were drawn on the bonnet, and their intersection defined the viable points for a particular actuator. These points were then input into a load model to determine the exact loading mounting positions that at the minimum overall load during the entire cycle of opening and closing of the bonnet. In this way, the optimum mounting point of our actuator was estimated. Powered bonnet modeling is done in Simulink using physical and electrical component blocks from Simscape Electrical. First, a linear actuator was modeled, which was further developed to give control features similar to the Cytron controller. We have used PI controller along with sigmoid input to control the opening and closing of bonnet. Sigmoid input is used to ensure smooth jerk-free movement of the bonnet. Plots of actuator load versus cycle time are shown in this slide. The figure on the left shows the load profile for the 14 kg bonnet with the maximum load of 610 newtons, while the next figure displays the load profile for weight from 9 to 14 kgs. Plots of angle of opening of bonnet versus time for a single cycle is shown in the figure. The maximum overshoot of 48.9 degrees was observed in 9 kg case, which is well within the 1 degree limits of desired output. Power consumption plot with different mass of bonnet is shown in the figure. It comes out to with 300.3 joules for 14 kg case. Also, power consumption plot is observed to be almost linear for mass 9 kg to the 14 kg. The mounts are made up of AI 3003 and under the most extreme conditions of loading as per our design. The minimum FOS came out to be 1.34. The mounts can be mass manufactured using the CNC machining technique. The simple design of the mounts ensures that the cost of CNC machining does not go very high. These mounts will be welded to the chassis and the bonnet preferably using TIG or MIG welding. Next, coming to bill of materials, we were able to keep the cost of all the components. We were able to keep the total cost of all the components under 20,000 rupees. Also, all the components used are readily available in the Indian market, targeting the mid to high-end car segment. The cost for this feature is quite manageable considering the performance offered by our design. It also contains the potential for the company to keep a good profit margin while offering these features to the end customers. The claim points based on our self-evaluation is tabulated in the following table. Listed on this slide are some references that we used. And with this slide, we come to end of our presentation. Thank you for your patient listening. We are now open to questions.
Can you please go to your slide
Okay,
number
so now
19,
we can
please?
move on to the Q&A session. And I just want to confirm that, please note, judges, that this is team number 8. Yeah, now we can go with Q&A.
Yes, sir.
Yeah, Aditya, can you go to your slide number 19, please? Again, you went very quickly.
Okay.
All right.
Okay, so shall I go for the first question, or does anyone want to start?
Yeah, you can start with it.
Yeah, you can.
Okay. Okay, so the way you have developed the system after you selected that linear actuation would be the best is really good. But my question is, how did you arrive at the idea that linear actuation would be the best way to go? And other than the uh, more number other than the criteria that you mentioned, that in the slider mechanism that you had seen there were more number of components, what were the other things that you thought that would make this not suitable for this mechanism? So I'm a bit confused that how did you arrive at linear actuator directly, like what were your thoughts?
Actually, first, like we thought of using a DC motor, but actually after researching a bit, we came that linear actuator is also like a DC motor, and we use some worm gears to actually make it linear. So if we in spite of uh, like using linear actuator, if we use the DC motor, then we have to make all those like mechanisms by ourselves, and it will increase the cost and like assembly, and it will also make it a complex process.
Okay, so just a follow up on that. So were there not any other ways? So you mentioned that there was a worm
Sorry,
gear.
uh,
Yep.
is the voice cracking for everyone or is it my network? Just wanted to confirm.
Mm, I think Divyanshu's voice was clear.
Okay.
Um,
In the meantime,
yes.
what's the, am I
Is
still
is
not audible to you?
Am I audible, sir?
Yeah, you are
Yeah,
to
Aditya,
me.
you are audible. Yes. But
Yes.
still, I think your network looks a bit poor.
Actually, I also wanted to add one point. Am I audible?
Yeah, Gautam,
Yes,
please go
please go ahead, God.
Yeah. So for the main idea for the linear actuator was that we wanted some kind of feedback system, so that we would be able to implement those safety features and the ergonomics and everything within our within a compact space. So that potentiometer feedback of, part is usually only available for linear actuators with that potentiometer feedback or Hall sensor effects. It is not available in other like push rods or tension or gas springs or other such mechanisms like that. For the slider, why we rejected the slider crank, Shubham can tell on that.
Yeah, so am I audible?
Yeah, you are.
Yeah, so the most significant reason we rejected the slider crank mechanism was as you can see in the slides, it is the larger number of parts and larger number of moving interfaces or joints where there are moving interfaces. So the manufacturing of these number of parts and its assembly and moreover its design as well, design optimization as well. If we combine all these factors and take it into account, the overall price for designing this mechanism will rise quite significantly. When we ideated on the linear actuator mechanism, direct actuator mechanism, that one seemed to be like very much more effective and efficient than this one, both in terms of power and cost as well.
Okay. Yeah, understood. Just a question here. So you mentioned that you mentioned the benefits of going for this linear actuator, but all these functionalities that you mentioned can be achieved with while using some external sensors as well, while achieving while having a possibility of getting higher efficiency or better ergonomics, right? So wouldn't it be a better approach here?
Yes, like the sensor is like sensor is like already fitted in the linear actuator. So like we noise will be very less in those sensor. If we uh, like fit external sensor, like it can be noisy, and like that's why we went for the linear actuator, and it will also like increase the VF assembly cost and all those things.
Okay, understood.
So Gautam, you mentioned about some safety features of like what are those in case of like any of these failure? Did you do any kind of assessment how it will how it is like kind of safe in terms of any kind of failure? Can you please explain on those?
The safety, yes, the safety features we talked about was this some kind of if we are opening the bonnet and if some kind of obstruction is there on top of it, maybe some kind of the object is kept on it or some kind of ceiling is there so that it is not able to open up to its full extent, where the feedback system within the potentiometer will be able to identify that and stop the bonnet at that point. Similarly, in the reverse direction, if someone is able to put put their hand in between the bonnet, maybe a kid or something like that, the actuator would be able to also detect that and stop at that point. So such safety features are already present through the use of the linear actuator.
Okay, good, thank you.
Yeah. So, do you also have the force curve for your bonnet motion?
Yeah.
So, can you please go to that? So, sorry, it's not very visible to me. The
Yeah.
legends are not clear to me. But can you tell me how many newtons of force you are expecting?
Ah,
Let's say in terms of the safety feature. So, let's say someone puts their hand and
mhm.
you want to stop your bonnet at the time. Okay? So before that sensor feedback takes, loop takes
Yeah.
place, what's the actuating force at the time?
So at the on the diagram on the left, the legend is not clear, but it goes from around 560 to till 610 newtons, and the actuator that we have selected has a range up to 1,000 newtons. So it can at this maximum point, it can also handle additional load of 400 newtons too. So it will be able to definitely be able to withstand the force that is put upon it up to a certain extent.
Yeah. So my question is regarding the safety. So you mentioned that you'll be using a feedback loop and stopping the motion of the bonnet if someone puts their hand there, right? So the force that you're mentioning is around 600 newtons, right? Which
at
is
maximum. Yeah.
significantly, yeah, so that's the force at the actuator, or at what point are you mentioning that force?
The at the is the this is for the steady state condition. So it is like during the entire opening and the closing cycle, the maximum force it will have to put on the bonnet would be 610 newtons.
Okay, so basically the actuator force.
Yeah, and also another point is that the static load it can handle is much higher than 1000 newtons, so 3000 or 4000 newtons. So there we have the greatest factor of safety around at the static points. That is for
Yeah.
the safety feature
So,
as well.
yeah, that's fine. So my question is, let's say you are closing your bonnet, and at that time someone put their hand. So how fast will your feedback system respond to that? Will it be able to stop? So it will the feedback system will respond when the bonnet is coming in contact with the hand, right? Or is
Yeah,
there
yeah.
any other
Actually,
thing?
sir,
Yeah.
we have also one more thing. We have incorporated IR sensor. So when
Okay.
anyone puts their hand into the bonnet, so that IR sensor will sense their hand and it will stop. That's the additional safety feature.
Okay, so the IR sensor is on the bonnet or somewhere
Yes,
else?
it's on the bonnet, like here.
Okay, this one. Okay, fine.
Okay. So talk. So on that IR sensor part, like a word on that IR sensor. So will the line of sight is sufficient enough, or how many IR sensor you have used, or you have covered
Uh,
that particular part?
like for this system, we have used only two IR sensors, and like for the first case, like if you have uh, bags or something in your hands, then
Mhm.
you can open your bonnet by using like kick gesture.
Okay.
And the second one is for the like safety feature, that's second IR sensor. So it's
So
shown in this
yeah,
figure.
yeah. So one IR sensor would be you think will be enough for covering the complete bonnet? Like let's say the child is having his hand on the extreme right. So will that IR sensor will detect that?
Like I think it can be enough. Like if we use the good quality sensor, there are sensors available in the market which can cover the whole.
Okay, so in that case, do you know the line of sight of for the IR sensor?
uh like line of sight, like it is not able to distinguish like closer than the 3 or 2 centimeter. So yeah, that's the drawback of this.
So basically, it's an angle that the
Yeah.
IR sensor covers.
Yes.
So have you taken that into consideration because it's a particular angle they cover, not the complete
uh
360. That's what
yes
I'm
sir,
saying.
sir, we haven't done this due to shortage of time, but
Okay,
that's the our basic
yeah,
idea.
no issue. Just keep that in mind. If in the future, if you are given the such problems, just keep that line of sight in mind.
Okay sir,
Just to add that.
sure sir.
Yeah.
So, so basically, for your safety features, you are saying that IR sensor is your primary sensor, which is responsible for your safety feature. So, where does the potentiometer comes into play? Can you please explain more?
Sir, sir, both can be used both can back each other. So
Yeah,
suppose like when
exactly.
it's closing and
Mhm. So,
when it
I'm not able to get
identifies
the
the
use of potentiometer as of now. So, yeah, can you explain me that?
so we know the curve of opening and closing. Like if there is any obstruction, then it will deviate from it, and the our system would identify it and stop the bonnet. So here comes the role of linear actuator.
Okay, it's basically a second layer
Like
of
if it's
protection after
yes,
the IR sensor.
yes, yes.
Yeah, and also the potentiometer is for if there is obstruction beyond the line of sight, if it is above the bonnet and something is obstructing it from the upward side, so potentiometer would also be able to identify that and stop the bonnet from further damage.
Okay.
A question from my side. So this TA23 actuator that you use, so like what's the fundamental idea? Is it what sort of an actuator is it? I know it's a linear actuator, but what mechanism does it use?
It is one gear mechanism. It is a one gear
Okay,
with a lead
okay,
screw.
so okay, okay, yeah.
and it has a Hall sensor for the feedback mechanism.
Okay. Yeah.
So one last question from my end, regarding the safety, or what I see is that a lot of sensors and automation sometime cause catastrophe. So what happens? Do you have any kind of input given when a car is kind of in a drive mode when it is riding, and this should not ever open automatically? This will lead to a very disastrous thing, right? Uh, any input in your diagram which you have created from either a wheel or engine or something like that, or open end input? Have you
Like
considered that?
definitely, if someone is driving a vehicle, this sensor should not work. So like this is for the like static position of the car.
All right, yeah.
Hmm.
One, if you can just go to the self-evaluation slide that you presented. So in that, you have mentioned that packaging you are claiming to be 24 out of 25. So from what I see in the linear actuator hinges, so it is covering a major portion of the bonnet. It is on the major length of the bonnet, right? So on the sideways, you will have shortage of space. You can't move some stuff in the sideways direction because you will have the arm of the linear actuator in that direction, right? So do you still think that it will be 24 out of 25?
Sir, are you talking about the side view of the bonnet? Aditya, can you go to
Yeah.
slide number 5, please?
So you had a 2D drawing, right?
Yeah, yes, sir. In this slide,
What's
side
wrong with
view.
that?
Are you talking about this one?
Yeah, this is one of them. So you had also shown a SolidWorks 2D drawing, right?
Yeah, that was a sketch mounting point
Sketch.
one.
Yeah, for the mounting
Yeah,
points.
this
Yeah,
one, right?
yeah. So what's the ratio of the this hinge length to the corner and the overall length
Yeah,
of the?
from that is a mounting upper mounting position length. It is around 200 and 220 millimeter, maybe
Okay, and what?
210 to 20 millimeter.
Okay, 210. Okay, then that makes sense.
I can actually zoom it here. All the dimensions are mentioned here.
Okay, yeah, fine. Okay, thank you.
Okay, so now we can move on to the next team. Judges, do you have any other questions?
No, I think that was all from my
Yeah,
side.
that was from my side as well. Thank you.
Yeah.
Okay,
Thank you guys. Great work.
Thank you.
okay, so now I would. Okay, so now team 5 can start their presentation. Please raise your hand. I will give you access. All the members from the team 5. Team 5, only 3 participants are there, right?
There
Hello,
would
am
be
I
one
audible?
more person
Yeah,
joining.
one more person, yes.
Yes. Uh, yeah. Okay, so total of 4 presenters. Sorry, 4 participants. Fine. Okay, means we can start then.
Okay, I'm sharing my screen. Just let me know if it's visible. Is it visible?
Yes, it is visible.
Okay, thank you. So, good afternoon to one and all present here. Today, we are going to present a solution for the problem statement powered bonnet for electric vehicles. The major challenges that we realized in this problem statement include the power consumption optimization so that the mechanism is light on the battery, efficient packaging of the component so that it doesn't affect the boot space available to the customer, reducing the cost of the components, and ensuring ergonomics like allowing manual opening and easy maintenance. We started with identifying the system requirements, followed by which we finalized the mechanism that satisfied our constraints. We have tunable parameters like the lengths of different links, the rating of the motor, using which we selected the off-the-shelf components, and based on the required ratings, the electrical and mechanical systems were finally simulated on Simscape to validate our design. And finally, the CAD was prepared, ensuring proper packaging and satisfying the required constraints. To automate uh, to automate the opening, holding, and closing of the bonnet, we propose a 3R 1P kinematic mechanism in which a crank is hinged on the base to the motor at a distance of 189 mm from the bonnet hinge of the bonnet. A cylindrical pin with a roller is attached on the other end of the bonnet, which slides in a slot along the bonnet. The motion of the crank is facilitated by a motor and a torsional spring attached on the crank axially along the motor. When the bonnet is open, the crank is past its dead center, and the weight of the bonnet pushes the crank towards the hinge, and this is how we achieve the mechanical stop. And because of the presence of this mechanical stop, the motor doesn't consume any power during the holding phase. The system that we propose primarily consists of four major components, namely the slot, which is mounted on the underside of the bonnet using bolts, a crank between the ground link and the slot, a torsional spring which is mounted on the crank axially along the motor and the motor itself. This mechanism is symmetrical about the midplane of the bonnet. Coming to the process definition, there are three phases. First is the opening, holding, and closing. As the bonnet just starts to open, the crank rests along the base with the torsional spring under maximum compression. As the motor is powered on, it is assisted by the torsional spring, which rotates the crank and in turn lifts the bonnet. During this phase, the crank travels by an angle of 154 degrees, which corresponds to 60 degrees of the bonnet rotation from the initial position. In the holding phase, the crank is rotated beyond the dead center such that a stable equilibrium is achieved, after which it is stopped mechanically to prevent any further rotation. And because of the mechanical stop, we do not have the need for motor power. Lastly, in order to close the bonnet, the motor has to apply an initial torque to overcome the dead center, post which regenerative braking torque is applied, such that the motor's torque and spring counter the acceleration due to gravity and results in smooth closing of the bonnet. In order to determine the dimensions of the crank and the respective safety factor, we identified the maximum loading condition. Firstly, the crank undergoes pure bending when the bonnet just starts to open, and this force comes out to be roughly 181 newtons. In the second loading condition, in the final position, when the crank experiences a compressive force of 661 newtons, please note that these values were calculated for a 14 kg bonnet. Using ANSYS static structural and the diameter of the crank as 16 mm with aluminum 7075 T6 as the material, on ANSYS static structural, we determined the factor of safety to be 4.32 for bending and 15, which is the maximum value that can be reported by ANSYS in compression. Now, the entire model that we have prepared has been simulated using Simscape and Simulink modeling environments. We have used the CAD and parameterized the model using a MATLAB script, which ensures modularity. The electrical subsystem consists of DC motors and its controllers. The motor gets the load torque, and using the preset position reference of the joint angle, it generates the torque and gives the crank angle as the output to the mechanical model, which is then fed to the joint between the ground link and the crank.
This slide shows the actuator or crank angle provided by the motors and the respective bonnet angle. We can see that the opening and closing motion is achieved within 4 seconds as specified in the problem statement. You can see that the bonnet angle dips towards the end of the opening motion because the crank goes beyond the dead center so as to achieve a stable mechanical stop. The given plots depict the energy consumption through the cycle and the crank's angular velocity, respectively. We can see that a major chunk of the energy consumed while opening the bonnet is recovered while closing the bonnet through regenerative braking. Also, through the crank's angular velocity, it is evident that the jerks are very low, ensuring smooth opening and closing of the bonnet. And these jerks can be attributed to the occurrence of crank's dead center or the mechanical stop of the mechanism. Here we can see the actuator torque for bonnets of 14 kg and 9 kg respectively, calculated analytically shown in black, and the actual motor torque from simulations shown in red, plotted against time. The slight difference between the curves can be attributed to the friction of the system, which is not considered in the analytical equations. To analyze the net energy consumption of the system, we have obtained the energy consumed during the three phases of the cycle. It can be seen that due to the presence of the mechanical stop, the system doesn't consume energy while holding the bonnet in the open position. Further, due to the usage of torsional springs, we have reduced the consumption by 46% for a 14 kg bonnet. Lastly, we have designed the system in such a way that the motors can provide negative torque so as to recuperate energy while closing the bonnet. We have also presented the respective values for a 9 kg bonnet. From the open and closed position of the mechanism, it is evident that the parts are neatly packaged within the specified area. Coming to the bill of materials, the total estimated cost of mechanical components turns out to be roughly 1500 rupees, and that of the electrical components is roughly 6800 rupees. The grand total comes out to be around 8300 rupees. We have used the retail prices for off the shelf components and the industrial cost of those needed to be manufactured. Finally, our design is capable of minimizing energy consumption by recovering more than 65% of the energy consumed during opening. The bonnet the bonnet's movement is smooth and within the required duration. The cost of the mechanism has been optimized by using actuators of lower ratings and achieving mechanical locking without using extra components. Finally, the proposed design is scalable across a wide range of bonnet weights with the maximum up to 22 kgs, thus ensuring reduction in cost of manufacturing. This is a comparative analysis of our solution against few of the existing ones. Firstly, our system requires actuators of lower ratings. It can be opened manually. Our solution requires much lower energy to operate due to regenerative braking and assistive spring. And lastly, due to lesser components and lower ratings, the total cost of the system is reduced significantly. In order to judge the effectiveness of a system, we have identified certain failures and how our system is robust against them. In case the motors fail, the system can still be actuated manually. The motors are capable of lifting a bonnet weight of up to 22 kgs and hence will be able to operate under excessive loading conditions caused due to debris or snow. By ensuring proper packaging, restrictions to crank motion due to debris can be avoided. Finally, our mechanism is within 0.5 degree of the specified target and hence has sufficient room for mechanical tolerances. In the end, we would like to thank Jaguar and Land Rover for providing us an opportunity to work on this interesting problem. The detailed bill of materials, governing equations, and the manual load calculations in case of actuator failure are mentioned in the appendix. We would love to answer your questions now.
And now we can move on to the Q&A session.
Thank you, team. Thanks for taking us through the presentation. I'll start with the motor. So you mentioned that you opted for two motors, and I see the cost of your mechanism is quite low. So can you tell me what all aspects did you check while selecting the motor?
Okay, sir. So while selecting the motor, the first aspect was was the rated torque for the motor, since it has to drive a heavy bonnet. So that was one of the, and then a 12-volt motor was selected so as to fit in with the auxiliary system of the whole vehicle. So those were the two major things that were considered. That it should be a 12-volt motor, and it should have it should be able to provide the required torque for the mechanism.
Okay. Did you also look into the robustness of the motor or the reliability of the motor, and what's the life cycle for the
So, sir, there were
standard life cycle for the motor? Yeah.
yes, sir. So in the data sheet, there was mentioned a set of the data for life cycles, and from that we estimated that the motor can easily last for an average use of over 10 years. That is why we selected this motor.
Okay, and what was the reliability for the same?
So what do you mean by reliability? I'm not sure.
Means from the manufacturer, you might have some data on reliability as to out of, let's say, 100 motors, how many will sustain that life cycle. That is
Okay.
mentioned by
Okay.
the.
So So actually, they had mentioned two life cycles. One was the like 95 percentile life cycle, and one was the like 50 percentile. So 95% of the motors can sustain the 10-year like duration that I mentioned.
Uh, Okay.
So you mentioned like 10 years. Do you think like mentioning in years would be better, or like you can have a number of cycles? How many times, if you, for example, somebody keep on like opening this bonnet again and again every day,
Yes,
do you think that would be a
I
better
agree that
choice?
that would be better, but I actually don't remember the exact number of life cycles. Just to calculate the year, I had assumed that each day the bonnet is opened twice, so it opens twice and closes twice, and that goes on for 10 years. So that is how I like
All right.
estimated 10 years. I don't
Okay.
remember the
Yeah.
exact
Thank you.
number. I'm really sorry for that.
But it's okay. Yeah. So if you have done that, then it's fine.
Okay. So regarding your, you mentioned that you are looking into regeneration as well.
Yes, sir.
So have you made a comparison as to what will be the power regenerated from this mechanism
Yes, sir.
and
Sure, sir.
the cost? And is there any additional cost going in because you are including the regeneration
Okay,
in the
sir.
system?
So I'll just say first on the energy consumption analysis, you can see that for a 14 kg bonnet while opening with the torsional spring, it consumes an energy of 65 joules while closing it like recovers around 44 joules for a 14 kg bonnet. And like respective values are mentioned for the 9 kg bonnet with and without the spring. So you can see that even the spring is also helping to reduce the energy consumption. And as far as the cost towards the like additional cost towards regenerative braking is concerned, we already have to employ an H bridge and a controller for the H bridge to control the motor. So only from that controller and an addition in the code will be required for regenerative braking. No additional hardware components would be required for regenerative braking.
Okay.
So guys, can you take me to that closing of the bonnet part? Like, is it closing automatically, or we have to do it manually? I think I missed that.
No, sir. So it will
Hmm.
close automatically. The motor drives it. The motor drives and controls the speed
Hmm.
of the closing as well. Of course, it is for like you can say that it is falling on its own weight. The motor is just controlling its speed by like the downward force is applied from gravity, and an opening force is applied from the motor and the torsional spring. So
Yeah,
that
so
way, it ensures
hmm,
smooth closing of
hmm.
the bonnet.
So that also we were discussing with that other team also, the safety feature, which we have been a major concern for us. The safety of the closing, like let's say the bonnet is closing and there is someone is having his hand on the bonnet. He don't want to close the bonnet, or let's say the bonnet is closing and some child has put his hand. So are you dealing with
So,
that, or you have
sir,
planned it?
actually,
So
this
that
was one of our queries regarding the safety systems that we need to deploy. So
Mhm.
we got this query clarified, and like we were told that safety features, like we may not include it, but still we have prepared an understanding
we
for
have
that.
yes, sir. So we have a plan for that. So one of the things that we can deploy is a current sensor for the motors, and whenever something, let's say a hand is comes under the bonnet,
Mhm.
then the motor will need to apply
Mhm.
a much greater torque to close the bonnet. And as soon as the torque requirement increases, the current will increase, and that current sensor, like we can program it to in such a way that as soon as the current increases beyond a certain threshold, the whole thing can reopen. Like that way, the safety
Yeah,
can be
and
ensured. But
adding to that, we can use IR sensor or radar with a specified or required field of view, depending on what sort of area we want to cover.
yes,
We can integrate both of them.
Oh, okay, cool. Thanks.
Yeah.
You mentioned mechanical stop for the. Can you give me a more details for the mechanical stop for the closing of
Okay.
book?
Yes. So let's say in this particular phase, if you notice, like uh, as the motor, like it reaches the dead center, it is the 90-degree, and we push the crank slightly after that, 1 to 2 degrees after that, such that like since the crank is past its dead center and the bonnet will try to open, but the slot has an ending. Like the slot, if you can see this image, just a second. Yes, if you can see this image here, the slot has endings on both. The slot is closed on both ends. So if the slider reaches to that particular point beyond the dead center, so it won't be able to cross the slot. So essentially, this particular position is locked, and the bonnet and the gravity will always try to pull the bonnet down. So in this position, the mechanical stop comes into picture.
Okay, that in that case, there's a possibility that the bonnet might not go to the uh, complete closure position, right? So there is a possibility that they might still remain, let's say, few mm of gap between the bonnet and the bottom of the car.
So, sir, for just I'll just clarify what Keshav said. So the ending, there are two endings to the slot. One towards the hinge of the bonnet, and the ending towards the hinge of the bonnet is will prevent it from closing back when it is in the open position. But the ending towards toward on the other side, that is the farther end of the slot, farther from the hinge of the slot, farther from the hinge, that at that place, that point is not restricting the crank to move forwards. Like at that point we
Okay.
can let like I hope you understand me.
Yeah, yeah, yeah. I got that point. I'm talking about while you're closing the bonnet.
Okay.
During open, it is getting locked. That is clear.
Okay.
So during the closure, you're saying so. Is the torsion spring the only other mechanism that's allowing smooth closure of the bonnet, or is there any other
No,
mechanism?
sir. Due to the negative torque applied from the motor and the torsion spring, both of them are controlling the speed of closing of the bonnet.
Okay. Yeah. Adding to
Okay.
that, we have ensured that the torsional spring, like during the entire motion, whether it's closing or opening, the torsional spring is always in compression, so that it assists the motor at every point of time and like basically opposes the gravity, so to speak.
Okay.
Also, sir, just to clarify, like motor is in a feedback loop, so there is no no gap between the closing of the bonnet and the car, so it is closing to its fullest.
Okay.
Okay, so you have used a torsional spring or a spring mechanical components as well. Like, have you considered different operating conditions? Like, for an example, the car is operating in Dubai, and the same car can operate in very extreme conditions, like very cold condition in Canada. Will this the effect of spring change across these two countries? Have you thought about it?
Sir, in that perspective, I can say that like if we ensure the packaging of the components is done properly, as in while installing the components, then direct effect of the environment won't be on the system, and even then, like the spring will be manufactured using the required component, let's say steel or whatever material is feasible. So, and that manufacturing will take into consideration the environment that the vehicle has to sustain.
And also, sir, to add, if because of the environmental conditions, the spring constant of the spring changes, then also our motor is fed in with a feedback loop. So it will ensure that the bonnet closes to its fullest and it opens to the 60-degree which is desired.
Yes, and the bonnet has the power to do so. I mean, the bonnet is capable of providing the required amount of torque.
Yes, just to add, like yes, the motor has been taken with a additional torque, rated torque, and that way it can open the bonnets even in even heavier bonnets. So it is cross deployable across regions, across platforms. So that is one of the features of our mechanism.
Okay, yeah, thank you. Yep, no questions from my end. Anyone else have?
That's all from my side as well.
Yeah, that was all
Can we
from my
move to
side
the
as well.
next team or
Okay, okay then. Thanks a lot, sir.
Thank you
Yeah.
very much, sir.
Thank
Have
you,
a
guys.
good day. Yeah, thank you.
Thank
Great.
you.
Thank you, sir.
Next team 11, they can raise your hand. I will give you. Team ID 11 can raise their hand. I guess everyone has joined, or uh, is anyone left to join? Fine. You can start a presentation.
A very good afternoon, distinguished panels of judges. We, the members of Team 11, are pleased to present our take on the automated power bonnet problem statement through our solutions, results, and considerations. We first and foremost analyzed the problem statement and fixed our core objectives that were the angular position of the bonnet with respect to time, simplicity and versatility of bonnet, its power consumptions, ergonomic of the designed system, space occupied by the bonnet's mechanisms, and bill of materials. We then moved on to a thorough literature survey process, which helped us identify potential solutions that could be implemented with appropriate modifications. So, before the synthesis of the mechanism, we had to specify the basic requirements of our system. Apart from the conditions inferred from the problem statement, we added an assumption of zero angular velocity at the start and the end of the opening and return strokes to ensure a smooth motion. Using this assumption and writing the torque equations of the bonnet, we developed our governing equation. And one important thing to note is that these equations are independent of mass and can be used in any mechanism. These governing equations and the given conditions were solved as a curve fitting problem, a popular and commonly used statistical mathematics tool to find a best fit function. Our notion behind trying Fourier was that it could give us a general function, but the resulting graph did not provide a smooth result. Since start and the end position were at rest, it is evident that the polynomial function would be symmetric about half stroke time. It was found that the equations were well satisfied by a 6 power me- polynomial function of time for angular velocity. The 6th degree was chosen because it ensured a constant angular velocity for the majority of the stroke time. So, as explained earlier, the plot of angular velocity indicated by the yellow line starts and ends at 0 and involves a smooth change. As for the angular position, the start and the end angles are achieved in one smooth stroke. Different mechanisms could be used to generate rotary motions. We consider using 6-bar mechanism and hydraulic actuators, which were discarded due to various complexities, high volume, and other inefficiencies. We also considered the use of electric linear actuators using Simulink. The linear actuator problem was solved entirely for a various actuator selection parameters. Actuator and controller satisfying these given conditions are custom made and cannot be implemented using the marketplace solutions. This solution may be further explored when appropriate actuators are available. So finally, an executable mechanism required for the application was determined to be a crank rocker mechanism. The mechanism was based on constraints like Grashof law and the spacing limit provided. It would additionally have to permit the attachment of a motor controllers, and gearing systems if required. We also have to make a sufficient clearance to prevent wear and tear. The force kinematic analysis were done using the free body diagram to determine the torque requirements and the angular velocity relationship, with a reasonably approximate assumption of a massless link. The system governing equations have been derived accordingly. It resulted in a relationship between link length and the torque angular velocity values of the crank link, determining the Bonder selection parameters. So now I hand it over to my other teammate.
Now that we are done with the preliminary analysis discussions, let us move on to the more important sections of simulation and synthesis. The design of the 4-bar mechanism discussed can be modeled as an optimization problem. For instance, when the initial configuration and the mechanism dimensions are optimized such that it minimizes the value of the maximum torque required in one complete cycle, then the ideal solution is achieved. To be more precise, the input torque requirements are reduced, thereby simplifying the motor specifications. By selecting certain parameters such as initial configuration, clearance, and path generation, we have built a near ideal model on SolidWorks. The fact that it satisfies all our requirements within the bounds of the given constraints holds true to the fact that the deviation from the ideal case it might be low. Coming to the most important part of our submission, a complete comprehensive generalized Simulink model, which models our equations, requirements, mechanism, transmissions, and governing equations. While developing the Simulink model, our key objectives were to compute the torque required so that the curve-fitted motion can be generated, to represent the 4-bar mechanism in terms of its critical parameters such as configuration and linked lengths, and also to specify a gear ratio and compute the same if required to modulate the torque requirements. Now let us take a look at the Simulink model. As dictated by the problem statement, we set the moment of inertia of the bonnet, mass of the bonnet, opening stroke time, stalling time, closing stroke time, as well as the mechanism parameters as workspace variables. These can be changed at will for various design related computations. This becomes the single most handy feature of our Simulink model, that it can be deployed into real production analysis by changing the values according to the requirements. The default configuration in the Simulink model that has been submitted has adhered to the problem statement conditions as well as our CAD model dimensions. We can see that the Simulink model is capable of generating all the required data as well as critical important plots. Now let us look at the compound gearing as explained earlier. From the Simulink model, as explained, we needed to modulate the torque requirements. So we went for a compound gear train. Compound gear trains, as we know, are compact in nature, maintain exact ratios due to no slip, and are capable of transmitting high power. As you can see, the teething for a 14 gear ratio compound gear has been done, the value of which will be explained in the subsequent slide. To explain the working, let's take a look at the animation on this slide. The motor drives the compound gear train consisting of 4 gears, which in turn drives the crank, which rotates the coupler, and finally the motion is transmitted to the bonnet as required. Let's take a look at how our motor selection was done. The Simulink model can be run for different values of bonnet mass as stated earlier. The 14 kg mass was run for different values of gear ratio, and the motor selection parameters were tabulated as shown. Using this table, for the 14 gear ratio 14 kg bonnet mass combination case, a single motor was isolated from the Indian marketplace and selected as shown in our bill of materials. The parameters taken into account for motor selection were torque during motion, stalling torque, maximum power required, and maximum angular velocity. Here is a look at the power input to the crank versus time. During stalling, since the angular velocity of crank is 0, the power input remains 0. Coming to energy calculations. Our critical objective while calculating the energy required for our mechanism was to calculate the energy at the primary battery level so as to get a clear idea of the overall solution. So by taking into account values of typical efficiencies of DC to DC converters in electric vehicles as well as DC motor power transmission, using the formula shown on the slide, the hand calculated value of energy turned out to be around 108 joules for our mechanism. Apart from the various mechanical considerations as discussed earlier, the ergonomic aspects of the problem statement were looked into deeply as well. They were analyzed, and finally, certain essential elements such as safety, minimum space utilization, and ease of use were integrated into the model. Here's a look at our bill of materials, which consists of components from the Indian marketplace as well as certain custom manufactured components. Using the vendor quotations on their websites and certain approximations based on past experience of manufacturing costs, the cost of implementation of this mechanism was estimated to be around 16,785 rupees. Here's a list of the references we had to use, the links and documents of which have been submitted earlier. For a quick recap, I'll just run you through our working principles. We analyzed the problem statement, conducted a thorough literature survey, derived the governing equations using curve fitting, explored the potential mechanisms and finalized the 4-bar mechanism, did the analysis of the 4-bar mechanism and isolated its governing equations, fed that equations into a simulating model that was generated for various data requirements, analysis of ergonomic aspects and integration of these elements into the model, and finally, an appropriate bill of materials was derived. This brings us to the end of our presentation. I hope that we elaborated upon the salient features of our model. Thank you, and we are open to questions now.
Yeah, thanks, Steve, for the presentation. So you mentioned that you selected. Can you please explain me the process of selection for why you selected gear, this such complex gear mechanism for this particular problem?
Right, sir. I'll take that question. So our simulating model was initially run without using a gear ratio or transmission ratio, and we could see that the torque requirements were quite high. And while going for a gear train, if we had used a simple gear train, which would be simpler in mechanism, but the dimensions required for the same gear ratio would be higher, and the number of teeth and the diameter of the gear would go high, and then that would result in our mechanism not fitting in the space provided. So compound gear trains are more compact in nature and could achieve the transmission ratios as required.
Okay. And why did you go for? Did you consider the other mechanisms such as linear actuators or so? As you saw it from previous two teams, they also saw. Okay, yeah, we made a comparison there. Okay.
Can I? Yeah, I'll just continue. So yeah, we consider linear actuator. We actually made a Simulink model too. So yeah, we have considered other mechanisms too.
Okay. So, what was your primary criteria for selecting this particular mechanism? So, I see a lot of numbers there.
Yes, sir. As explained, we tried the 6-bar mechanism and hydraulic actuator, which were directly discarded due to their complexities, inefficiencies, and high volume. Now, coming to the linear actuator, this problem was explored slightly more. We ran the Simulink model, and to see that linear actuators are actually used in existing tailgate solutions, but here our situation is a little bit different. We have a higher mass, and we are required to generate a particular motion within a given time frame. So this would result in a load speed characteristics of actuators, as mentioned here, the maximum velocity and the maximum load coming on the actuator. These are not compatible with existing actuators. So we had to look into a furthermore simpler mechanism which could be achievable using better control. And hence, we had to move on from linear actuator to 4-bar mechanisms.
Okay, understood. Thank you. Just one more question. So, can you go to the image of your mechanism? Yeah, this one. This is also fine. Yeah. So, can you please tell me what's the ratio of distance between the hinge for the bonnet and the hinge for the actuator? Distance between those two and the length of the bonnet.
Okay, I have the values actually. So our distance from the hinge to the bonnet link is 364, and from hinge to the motor, the what do you say, the what do we call that? The distance between the hinge and the axle of the motor. Yeah, axle of the motor, axle of the gear is 122. 122.
Okay.
The entire mechanism was designed in such a way that it fits into the space provided.
Okay, because that's where my question was going, whether it's fitting in that space provided or not.
Yes, sir. Yes, sir.
From the image, it looks that it's going out. So, yeah, just wanted to confirm that.
The hook that is attached to the bonnet that is at the longer side, but we have made sure that that fits in the space that you wrote in the problem statement.
Okay, thank you.
So that has also been depicted in the submitted CAD model. It can be verified.
Okay.
So regarding the safety of this, like the entire mechanism, like what have you considered altogether? Like, like what kind of things you have considered?
Okay, so I'll take that up. So uh, the safety part, we thought of putting IR sensors, but we didn't work upon that because that comes a little under control side. So we could have explored it more, but uh, we weren't sure if that is the what do you say?
Elaborate further upon that, apart from the control side for the safety, we have ensured that the mechanism is as slow as possible, and physically the mechanism does not consist of any sharp components which might harm the user.
So how many IR sensors you have used in the design currently?
So I'll be taking that question.
Yeah.
In the problem statement, we were given that the main aim of our problem statement is to create a mechanism that will successfully open and close the bonnet within the given stipulated time and create a smooth motion for which can be controlled without the manual power used. So our focus wasn't on the on the control, how the
Safety
whole
side, yes, yes.
yeah how the whole mechanism would be controlled, but rather the mechanism and the physical mechanism, how it would be shown. So we did research on some sensor. We can use a few sensors on the system, but we didn't go that much into the research part. We know we can use higher sensors for we can place them on the bonnet, and that would create uh, we can use a stipulated amount of 32 sensors could be used, and we can then create a safe model for the um, system. But we weren't that much concerned about the whole safety and the control mechanism, because the main problem statement wasn't aimed towards that. So still we did some research.
No, no, it completely makes sense. No issues with that.
One more question from the side, actually. So, does your system also have any mitigation? So, let's say for some reason your motor fails. Okay. So, is it does the user or the driver has any other ways of opening or closing the bonnet in that case?
Yeah, I'll take that up. Yeah, he can manually open it. So
So,
there's no issue
how
in that.
can they miss? So, how much? So, it is still connected to that motor, right? So, there's no
Yeah.
disengage from that motor. So, they'll have to overcome that motor torque, basically, right?
The motor will not be having power, right? In failure mode.
Okay. Okay.
It will
Which
not
type of
provide.
motor is this?
This is a DC motor.
Okay. Okay. Understood. Just one more thing. So you have put a stop, this red stop in this current image. Uh, Red stopper for the open position of the bonnet, right? So wouldn't that be a critical component? Means a failure, prone to failure component there, because the cranks and that stopper will continuously coming in contact each time you open them. And looking at the size of the crank or the width of the crank, those two components might be susceptible to failure, right? So have you done any
Yeah,
study in that?
actually, yeah. So what we are doing is we are making sure that the velocity becomes zero at the stopper. So we have taken omega that way. So the chances of that happening is very low.
Okay, understood.
Uh, Also, sir,
Okay.
that stopper that is shown in the image, that is just for the representation. Uh, the, s- the dimensions and the shape of the stopper will not be the same when the model will be implemented. It will be implemented in the body of the vehicle only.
Okay, just to continue the question which was asked regarding the failure, right? So you said you can open the bonnet manually, but how would you lock the bonnet at a position now, because now the motor doesn't have any like it's freely moving.
Sir, I'll take that question. So the problem statement was intended towards automatic powered bonnets. So that's what we have done here. But for a manual mode, as a backup, we may use support struts as used in the current bonnets, which can be manually attached to the latches. So it's just a question of adding extra latches to the end of the bonnet so that the support struts may be engaged manually. That would just be a backup.
Okay. Yep. Thank you.
Judges, do you have any other question, or we can move to the next team?
I think we are, no from my side. Yes,
That's all
we
from my
can move.
side.
Yeah.
Okay, so next team, team ID 10, you can raise your hand.
Thank you.
So, am I audible?
Yes, you're audible. I guess all
Yeah.
the participants have joined. Okay, fine. Yeah, you can start.
Okay. Good afternoon, everyone. We are team number 10. Here we are about to present a solution for the low prep problem of powered bonnet for electric vehicles prepared by JLR as part of Inter-IT Tech Week 10.0. Speaking broadly, we have covered the following topics such as the design and the simulation models of our mechanism. Our problem statement was to simulate the working of a powered bonnet for an electric vehicle. We shortlisted a few parameters considering which a design had to be made, some of which are affordability and design simplicity. As mentioned in the problem statement, there has been some research in power tailgate systems that mostly used actuators. But actuators tend to be costly and any maintenance is done by replacing the whole assembly. After going through some papers and designs of mechanical hinges, we tabulated the features of the following three design systems. Starting with the dual actuator mechanism, this is commonly used in regular cars, which use automated dampers. Moving on to the next system, the 6-bar linkage mechanism. It's a variant of the 4-bar linkage system and is very complex. The worm and worm gear mechanism is our proposed solution to the design problem. So why did we choose this as our solution? The major features that support choosing the worm and worm gear mechanism were cost, complexity, number of moving parts, and repairability or ergonomics. For example, in the case of repairability, we have two mechanical links and a worm and worm gear attached to the motor. These are fundamental components and hence cost efficient and easy to replace. So how does our system work? We have a DC motor powered by the car's auxiliary 12-volt power system, which is run through a worm and worm gear mechanism, which reduces it sufficiently to have enough torque to rotate the linkages and lift the bonnet. A feedback system is added to regulate the opening and closing of the bonnet without any jerks. We have done a physical modeling of our system in Simscape. As is evident from the picture, we have used rigid transform to add various mechanisms to our system, such as the worm gear mechanism, the mechanical links, and the bonnet, and got the angle versus time graph of the bonnet. The input is provided to the worm gear, which is connected to the mechanical links. These mechanical links translate the torque to the bonnet. Worm gear is used to convert the torque provided by the motor up to a sufficient amount, which is further used to lift the bonnet through the mechanical linkage. We have used the worm gear mechanism because it can be rotated through the worm only. So if we do not rotate the worm, the bonnet will remain at a fixed angle without any energy use. Here we have shown the front, side, and isometric view of our CAD model. This is the worm wheel and this is the worm gear. These are the mechanical linkages that connect the worm wheel to the bonnet here.
One of the significant advantages of choosing this mechanism is that in a 2D environment, we will get a classic 4-bar linkage mechanism. Since this is a simple standard system, which is well studied and documented, we do not have to worry much about its working in the physical world. Next, we decided the lengths of the links and the torques required using an iterative procedure, which involved the simulation of a 2D model. We started by deciding the rough limits of the link lengths. We then iterate over the lengths of the links and calculate the required torque. We then compare these torque values to find the lengths of the most efficient linkage systems. This is a simulation of the simplified 2D model, which clearly shows that the model is working with the shown lengths. The line AC is the bonnet, while CE and EB are the first and second mechanical links respectively. Our next goal was to find the torques required by the motors using the governing equations. These are the free body diagrams using which we obtain the governing equations shown here. This is the angle versus time graph of the bonnet. We have restricted the moment to 60 degrees from the initial position, that is 12 degrees below the horizontal to 48 degrees above the horizontal. The cycle starts at time 1 second, and the bonnet opens within 4 seconds, stays open for 3 seconds, and closes again in 4 seconds. This is a plot of the torque required from the motor versus the angle of the bonnet. This is based on the governing equations mentioned in the previous slides. This is a graph of the power consumed versus time in one cycle. As is evident from the graph, our model only consumes power when the bonnet is opening or closing and consumes no net power when it's fixed at an angle. Again, this is possible because of using the simple worm and worm gear mechanism, which has a self-locking feature. After the simulation, we found the bill of materials, starting with material selection. Based on load-bearing capacity, we have shortlisted aluminum and steel. We have included a comparison between aluminum and steel and finally chose stainless steel AISI 1018 as a final material. In addition to these figures, we also know that aluminum is not easy to work and leads to faster wearing of tools. We then went on to motor selection for our model. We needed a motor that is easily controllable, can absorb sudden rises in load effortlessly, and have high starting torques. These are the characteristics of a DC motor. In addition to this, we required a motor that can provide high torque at low RPM. So we used a planetary gear DC motor that can go to lower RPM than a general DC motor. These are the parameters for our motor selection. We selected the PGM 45775 planetary gear DC motor from Orange Motors. as a mechanism driver and use an Arduino controller system to get the optimum output.
Now comes the bill of material of our model. This is the bill of mechanical components. As mentioned, the cost of mechanical components that include the gear systems, the linkages and joints is about rupees 3000. This is the bill of electrical components. The cost of electrical components include motor, motor controlling system Arduino and photo encoder, which comes to be about rupees 6300. The final cost is rupees 10,000. Miscellaneous costs include small equipment like push buttons, bearings, machining costs, etc. As you can see, this amount is less than half the cost of a fully electric liftgate system available in the market. This is the SWOT analysis of our model. The primary strength of our model is affordability and simplicity. Using a worm and worm gear mechanism gives us a mechanical advantage that rotating the worm wheel will not move the worm gear, and hence the bonnet could be held at any angle possible. However, our model is a bit exposed and can be improved by introducing a casing. Pushing to the ergonomics, we have thought of keeping a push button, pressing which starts the bonnet opening process, and pressing it again stops it. Since the mechanism is at the edge of the bonnet and consists of minimum moving objects, it is easily repairable. As we have mentioned in the thread section of our SWOT analysis, our model fails in the case of motor failure. To solve this, we have also introduced another rotary shaft, which is possible because one end of the worm gear is free of any connections. This makes the bonnet opening manually feasible and reduces the dependency on automated systems. These are the resource links which we have used while making this project. And it concludes our presentation. Thank you. We are open to questions.
Thank you, Dave. Thank you for the quick presentation. So, can you just explain? At the end, you mentioned you explained that you have kept a secondary mechanism for to allow manual opening or closing of the. So, can you please explain this mechanism?
Sir, actually, we have kept the motor in front or below the gear mechanism. So, what makes introducing this rotary shaft feasible is that there are two ends to the worm gear, right? So, one end is connected to the motor, and the other end is free to rotate. So, what happens when the motor fails? So, as we have used the worm gear mechanism, opening and closing the bonnet is not feasible in that case. The only way to open the bonnet is by rotating this worm gear. So we have introduced a rotary shaft which can be rotated, which we have thought of keeping it in near the dashboard or somewhere where it is possible for the person to access it, so that in the case of gear failure or in any gear failure, in any motor failure, the shaft can be rotated and the bonnet can be opened at any angle.
Okay. So yeah,
And
understood.
to elaborate further, since we have used the worm gear mechanism here, so it doesn't matter that the bonnet has to be opened to the maximum angle or to the minimum angle. It can be opened to any angle. It depends on how much we rotate the rotary shaft. Thank you.
Okay, thank you.
You mentioned that you have a mechanism to open via push button, right? Can
Yes,
you
sir.
please go to that? Uh, so, at what location this push button you have kept?
So actually, we were thinking of keeping it near the dashboard again. So other places might include, we also thought of keeping a wireless mechanism, but that needed time to analyze that feature. So we have thought of keeping it near the dashboard.
Okay, so this is like kind of electrical system kind of
Yes, sir.
thing, which okay, all right, yeah, thank you.
Sorry, if I just wanted to make sure. So you are allowing the opening of bonnet or function of the motor while this button is pushed, right? Only for
Yes,
that
sir.
period of time.
Mhm.
And as soon as you unpress the button, the motor will stop rotating in whatever position the bonnet may be, and it will stop there.
So actually using like there are different kind of switches available. So one of the mechanism which you explained is exactly what we have thought of. Others are also feasible.
Okay, and how will you differentiate whether the driver want to further open the bonnet or further close the bonnet if it's in a, let's say,
Yes.
middle position?
So actually, there we have like thought of the push button. I'm sorry, the push button has three kind of uh, positions where the button can be pushed. So, like in the initial position, when we push the button, it will open, and when we press it again, like with a greater force, it will like go inside. And depending on like if we want to close it or open it, we can like uh, push the button again and bring it to the middle position. And
Yeah, fine, understood.
So don't you think this will complex users' life and they will be frustrated if like they're not they have to do it again and again? Can it be like further simplified? Do you
yes, sir.
think
There
that?
is. I'm sorry to interrupt. Yes, sir. This like the push button feature can be further simplified. We agree. This is also included in the opportunities in our SWOT analysis.
All right. Yeah. Thank you.
And what's the time as per? Uh, so let's say your bonnet is in completely closed position, and let's say the driver pushes the button to open it. Okay, so what's the total amount of time taken for the bonnet to reach its maximum open position?
So 4 seconds.
4 seconds. Okay. So in that case, how will you make sure that when, let's say, when the bonnet is coming to a closed position, when it is coming in contact with the other parts of the car, it doesn't. If it is moving at a constant angular velocity at the time, so uh, how will you make sure that it doesn't create any impact or doesn't damages other parts?
I'm sorry, sir. Could you please pardon?
Yep. So you're saying that so you don't have any controllers, right? So the push button is the only controller that is there. So as soon as you push the button, it will let's say bonnet is open and it will start moving down. So how will you make sure that when it is closing, the bonnet is closing at the time it is not colliding with other components at a significant angular velocity and not damaging them?
Sir, I would like to take that question.
Yeah.
Sir, for that thing, we used a photo encoder encoding sensor which measures the angle and send the signals to uh, the motor control system, which then regulates the RPM and power output of the motor. And once it comes near closing situation, that is the minus 12 degree from horizontal, then the motor will provide less power and will reduce the speed of the bonnet so that it does not cause any impact on any of the surfaces.
Okay. So yeah, fine, understood. Yeah. Thank you.
Okay. I do not have any further questions. Does anyone have?
That's all
Okay,
from my
so
side.
we can move on to the next one. Oh, do anyone have any doubt? Okay, so we can move on to the next team.
Thank you.
Uh, yeah, team ID 16. You can raise your hand. I just want to confirm Team 16, every participants have joined or still someone is remaining?
Yes, ma'am, everyone is joined.
Okay, fine. You can start with the presentation.
Yes, ma'am. Uh, Anshuman, can you confirm my screen is visible?
Yes, yes.
So, good afternoon, judges, and everyone present over here. I am Govin from Team 16 presenting our solution. So, before going into the presentation, I would like to discuss about the problem statement given to us. So, the problem statement given to us is to automate the bonnet of an electric car. So, with this problem statement, we have given four targets like to open the bonnet to 60 degree and to open the bonnet in a 4 second and closing of the time is also a 4 second. The bonnet should remain in static position without any manual support after the system is off. And the next thing is the bonnet should closes in a safer manner. So, to tackle this problem, we have gone through the analysis of all the component and resource and tools which are available in the Indian market. So, we at last after the analysis we come to use of high-speed linear actuators. So, this is the outlook of our whole complete solution. Uh, the first stage is of user input. The user will give the input to the control unit. The control unit is basically here is the node MCU which we are using. The control unit will give commands to motor driver based on the feedback it get and the user command it get. So motor driver basically controls the linear actuator and the linear actuator will automate the bonnet. So here the potentiometer act as a feedback which is an inbuilt potentiometer inside the linear actuator. So you might be wondering why we taken the linear actuator. So as I already told that we have gone through the all resources and tools present in Indian market. So we came up various other resources like using servo motors or using stepper motors which have much faster and greater action. But the problem with those kind of actuators are like the size and the cost increases as the load increases. So therefore, after going every analysis like in price and efficiency and everything, we have like a selected linear actuator is the best suitable tool which can solve our problem. The next thing is this is our circuit diagram. So you can see the motor driver is connected to linear actuator with a 12 volt DC supply. Our linear actuator will be of 12 volt. Actually, while solving this problem, we expanded our domain, not only restricting to the electric vehicle. We wanted it to be applicable to every cars present in the market. So the controller you can see here the figure is of Arduino Uno, which is very much similar to Node MCU. So this is the circuit diagram, and the next here you can see this is our accepted output. So you can see the bonnet is lifting through the help of linear actuator. So coming to the next, linear actuator was a tool we wanted to use, but how to find where exactly we wanted to mold it. So we were given in the problem statement that we have a radius of 40 centimeter working space and 15 centimeter as a depth. So, giving that constraint and keeping that in mind, we have we have hinged one point of the linear actuator on the hood, and the next point is find it out by using the two stroke length of the linear actuator. When the stroke is at zero, one circle is drawn, and the other circle is drawn at the maximum stroke, which is of 12 centimeter, and the point of intersection of those two circles give us the hinge point for the linear actuator. So in this way, we have optimized the position where we want to hinge. After getting the hinge points and after hinging the linear actuator, we did this calculation using our geometry in the SolidWorks. So after calculating, we got the maximum torque for lifting is which is equal to 62.792 Newton meter, and the load acting on our linear actuator, which is equal to 137.66 Newton. So next, I would like to call my teammate Anshuman Tejasvi to continue this presentation.
Good afternoon, all judges. Let's proceed forward with the CAD model. So here in the left, you are seeing the CAD model that has been shown in the rendered mode. It is basically a soft prototype of our physical model that is going to be implemented. Here you can see how the actuator has been positioned according to our calculations, and to make more clear to our simulations, let's see this is a short video of opening of the bonnet according to the constraint of 4 seconds. In 4 seconds, the bonnet is opening from its initial position toward angle of the constant value that is provided to us. Now, moving on forward, we have used the SimScape simulations. First, the model was created and totally been designed in MATLAB. Sorry, in SolidWorks. Now, to proceed all with physical constraints, we have just proceeded that model to MATLAB SimScape. Now, all the physical constraints are applied, all the geometrical constraints are applied, and now simulated to get the optimum result. After just sequencing all these formulations, we got the optimum solution of the in the video format. As you can see, the bonnet is going down in 4 seconds and also moving up in the 4 seconds without any jerk. As the main motive of our was to just reduce the jerk as much as possible, and to make it all this done in a time lapse of 8 seconds. That is 4 seconds of opening followed with the 4 seconds of closing. For a better idea, we have just plotted the velocity versus time graph of the bonnet. Here you can see for the first 1 second. For the first 1 second, the velocity was constant for a particular value. Then it has been optimized to a dynamic value so as to just reduce the jerk. Now in the last part also, that is about the 3 second, again the velocity has become constant. It has all the calculations are based on some certain geometry, as the calculations have been previously mentioned in slides. Now moving on forward, this is our angular displacement versus time graph. So you see for the first 1 second it is about linear, and in middle it is about the curve, as it is in the middle part the velocity is in dynamic nature, and also in the last 1 second it has again become a straight line. Now the prime focus of our model was to easy implementation and cost effective. So, keeping in that mind, we have used a 12-volt linear actuator that and various other modules like Arduinos and other control drives, and giving a sum of only about 3,763 rupees for a product that can easily be implemented to any vehicle, whether it is an electric vehicle or simple IC engine vehicle. So we have not mitigated any constants to apply all these. Now, why our product should be used and what is what to say, the uniqueness. So first uniqueness is, yes. Yes. So the first uniqueness was that it is very much cost effective. As you have seen, in only about 3,700 rupees, we have developed the full model of the actuator system that can be implemented. Second part is it is very easy to use. That means it is very ergonomic. Third part, it can be commercialized easily as a product. Just we have to purchase that set of the modules and actuators, and can easily be implemented to any car bonnet with just a what to say, just a hinge point at the bonnet. Fourth point is that it is a single switch operations. That is, from single switch it can be opened in 4 seconds, and again for clicking that it can be again closed in 4 seconds. Nothing other is required to be given. Now further we are scoping to optimize this product as an IoT base. That means maybe you can do it as a smart vehicle operations or wireless operations. That can be more further discussed in our R&D operations. Again, moving forward, it is a very compact design. As here you can see, it is taking a very less space, and we have confined to a very small volume to be precise in the according to our constraints. That the volume should be as less as possible, so that the luggage area should be as great as can be, so that the users should not get any problem. And as I earlier discussed, that it can be implementable in any car, whether it is IC, EV, or anything, because it is very easy to use. So this is our sources from where we get helps and assistance in doing all these researches and model based. Hope you liked our presentations and liked our product. And we are very free to do the question and answers part, and we are very happy to give the answers to them.
Hello guys, great work. And just want to a quick check on whether the like you actually implemented that your system, or like as you shown in the third or fourth slide, I guess you basically implemented that, or what was it?
Oh, sorry, sir. Can you repeat?
Yeah,
Yes.
just if you can rewind back to your slides. In the fourth or fifth slide, you have actually there was a bonus shown there. So you actually implemented that,
No,
or
sir. Actually, that was a resource we got online.
okay, just want to confirm.
Uh, yes, sir. But we are in the process to implement it. In our college, we are trying to make it as a product. Like want to proceed forward in the problem statement.
How would you use that in the like in the college, like for the regular purpose, or some specific project you are working on with the college student?
Sir, actually, our college is more focused on product development, and we are seeing this model or this project as a product. So we want to move it like further. We want to like cost effective. We want it to cost effective, and like we want to implement in the market. So we want to take it as a project. So we have a NVCTI development product development center where we want to take this problem statement and want it to develop more. Like, we are not limiting ourselves only to this competition or interaction.
Can you go to the operation range for their? So you mentioned you described the velocity, angular velocity, as well as the position for there was next
Yes, sir.
slide. Yeah. So the next slide after this. So angular displacement of the point. So what in terms of the angular? So sorry that angular displacement. So it is you are taking it to 60 degrees, right? So what?
Yes, sir.
Which so you are starting from 0 degrees to 60 degrees. From the cats that I saw, so you had a certain. If you go back to your cat, please.
Yes, sir.
Okay, so your top surface is the for which is the surface for which you are showing that angle, right? 0 to 60 degrees.
Yes, sir. Yes, sir.
Okay, fine, that makes sense. Regarding the actuator, so I'm coming to the so since you mentioned very low cost for your system, so
Yes, sir.
you have taken 2,000 rupees cost for your actuator. So can you
Yes, sir.
please
Actually,
tell me the specification
we
about
were
that?
asked to. Yes, sir. Actually, we were asked to give everything proof. So that's why, like, we have searched to all the market suppliers
Yeah, that's
who
fine.
can
I just want
provide us.
to know the specification for the.
Yes, sir.
Actuator.
That's for that I will coming. So we have everything attached. So this is the linear actuator AX030. So this was the Energix Power Engineering Excellence is a company based Bangalore. So they were providing it for 2,000 per piece, and this is the specification of the motor. So the actual motto of selecting 12-volt motor is to that like we can implement in any car because car batteries come with 12-volt battery. So we have a rated load, like maximum load of 45 kg, at which it can move 3 centimeter per second. And for the static load, we have about 90 kgs.
What's the working load? Sorry, I forgot.
Yeah,
It's 45
it's
kgs, right?
yes, sir.
Okay, and does that satisfies your requirement? So
Yes, sir.
what's the
Actually,
bonnet
you
weight
have
that you
seen
have taken?
like it's about 450 newtons, right? And
Yeah.
as we calculated, uh, the slide you can see, we were getting a maximum load of 137.66 Newton.
Uh, yeah, if you can maximize that slide, I just
Oh,
want
yes, sir, yes,
to take a look at the calculation.
yes.
Four 56. Okay. The bonnet weight that you have used is
So 14
14
kgs.
kg. 14 kgs, right?
Yes.
Okay. Thank you.
A question from my side. This actuator that you are talking about, what is the fundamental like principle for this actuator? Is it an electromagnetic or it is the same like others mentioned,
Yes,
a
sir.
lead screw basically?
Yes, sir. It's a lead screw based with a feedback loop of potentiometer. So basically, as thread increases, the potentiometer tells us the stroke length. So for every second, we can get a dynamic data that how much lead has opened or how much stroke it has covered. So giving us an opportunity that with further development, we can modify it to a UI, a user-based interface where we can set our own set our own angle at which we want to open it. Since we are using
So
a node MCU, we can implement IoT also.
yeah, so a question like I get that the main target that you are going for is simplicity, but did you
Yes, sir.
look into other mechanisms and like other than keeping it simple, what are the main parameters that led you to think that okay, only a linear actuator is fine and other mechanisms would be like what are the parameters
So,
basically on which you
yes,
decided
sir.
that?
Actually, the first parameter we were looking was that it should be applicable to every cars, like not limited to EVs. So that's for that we have limited our power resource at 12 volts. And the second parameter we were looking was the cost effectiveness and simplicity. So for this we gone through a lot of mechanism, like we have servos, we have like rotating actuators which we can attach with gears and we can automate the hood, and we have stepper motors. But the thing is, so, like as the weight increases, like if I want to go for 13 kg and 14 kg with servos or a stepper motor, the cost increases. Approximately, it's like our linear actuator is of about 2000 cost. But as I was considering for the same thing in servos and steppers, it was going around 20,000, the 10 times of our linear actuator. So I wanted it to be as much as cost effective and as much as compact design, because as load increasing, the servos and the stepper motor size are increasing. Same case as the linear rotary actuator also.
Okay, yeah, that answers my question. Just a follow up. Were you guys able to look into some mechanisms that you rejected? The not the direct actuation. So servos and everything would go come into direct actuation, but like other guys are proposing, you could have gone for certain mechanisms where a motor or a linear actuator would just act at the input, and the final output would be based
Yes,
on
sir.
a certain sort of
Actually,
a mechanism.
yes, sir. Actually, we were looking gear a complete gear system, which is powered by a motor and which connected with the donut hinge point, bonnet hinge point. So the thing was that with that is like if any of the complete systems, any of the part fails in the complete system, we have to remove everything. So it made much more complex. Like for this is simpler, so easily can be maintainable. That's why we took this apart from going into the mechanisms.
Okay.
Yeah, go.
And in cost effect.
Sorry. Is it just me or is it frozen for everyone?
Yeah, he is frozen.
Yeah, connection lost for me. So if anyone else from the team can answer this question,
Yes,
so
yes, yes,
uh,
yes.
can someone show me the distance from the bonnet hinge to the hinge of this linear actuator in the PPT?
Just a second, sir, just a second.
Hello.
Yeah, you
Hello.
are audible
Yeah,
now.
Govind. You're audible now. If you can reproject the presentation.
Is my screen visible?
Yeah.
Yeah.
Yeah, it is now.
Yes, sir.
So over here you have given the T max of 62 Newton meter and the force required is 137 Newton, right? So you're saying that your hinge point from the hinge point of the bonnet and the hinge point of your actuator to the bonnet, the distance between those two is between about 0.5
456.74
meter.
mm, sir. Yes, sir.
Okay, it's that far. Okay.
Yes, sir. Actually, sir, I'm not able to get your question.
Yeah, no, I was just making sure that that's the distance between the two.
Yes, sir.
So
Actually,
is that the distance between the center of mass longitudinal distance or where the hinge point is?
so it's the hinge point where we fix the actuator, actually.
Okay,
So the
and
F
you are
max is calculated when it was at rest position on 0 degree angle.
okay. So and you're applying your forces on you're taking that as your center of mass as well because you're applying all your forces there as well, and your calculation that you have done are based on that particular distance only.
No, sir. Actually, the linear actuator we were using has a stroke length of 12. So, to getting that as a constraint, we needed to get a point where we can hinge it. So we got this as the optimal point where we can hinge, and
Sorry, so stroke length was how much?
so 12 centimeter.
12 centimeters. So okay.
For 0 to 12, it is going about 60 degree. We can customize it uh, as per our requirement. So
Yeah, just give me a second. So if you can go back to your CAD. Yeah. So from what I can see here, so the distance between the hinge of the bonnet and the where you have connected your actuator to the bonnet,
Yes,
those
sir.
2 point that distance I don't see, because the height of the bonnet itself is 1 meter, right?
No, sir. Actually, that's not the stroke length of 12 centimeter. Actually, the stroke length is basically
No,
when
I'm
it
not.
was.
I'm not talking about the stroke length. I'm talking about the distance between the hinge of wherever your actuator is connected to your bonnet. That hinge that you
Yes,
have
sir.
connected to C hinges, right? That, and the
Yes,
hinge
sir.
of the bonnet to the body of the car. So
Yes,
that
sir.
distance I'm talking. What's that distance?
Yes. So we have fixed it as per the
Not this.
maximum
No, sorry,
length
sorry.
of.
Again. Not that distance. Is there any way I can take control, or
No,
I
sir.
don't think so.
Okay, I can show you the CAD model in 2D of this
Hmm.
actuator.
Okay,
If you are okay.
let's call your points A, B, C. Okay, so
Yes.
let's go back
Okay,
to the
sir.
guide.
Let me again present it. Yes, sir.
Okay, let it open. Yeah, fine. Just pause it there. Yeah, just pause it there. Okay. Now your point A is wherever your 2C hinges are there. Can you take your pointer to that point?
Yes, sir. Yep.
No, not this one. The other. Okay, let's call this point A. Yeah, this is point A. Okay.
Okay.
Wherever you have this pointer, and the top part, let's call that point B. This is point B, and point C is where the bonnet is connected to the body. Can you take your pointer to that point?
Yes, sir.
So the entire line is point C. Let's call that entire line connection with the body. Okay.
Okay, sir.
Okay. So the particular distance from that line to point B, what is that distance? That's what I'm trying to understand.
Okay. The distance, sir.
Mhm.
In the calculation, so this one.
So the calculation, what you have shown is that 456 That seems to be the center of mass of the distance of the center of mass from the hinge of the bonnet, right? That
Yes,
still
sir.
seems to be the case, not the actuator connection point, right?
No,
So
sir.
your on actuator force will be
Yes, sir.
much
Yes, sir.
higher. Yeah. So
Yes, sir.
your on actuator, so distance between your actuator hinge and the line distance that I was saying, so that will be much smaller, right? It will be, might be less than 100 right? So
Okay,
the
sir.
on actuator force will be much higher than what you have calculated
Yes,
here.
sir. Yes, sir. Yes, sir.
So
So, but
that will,
it won't be crossing up to 45 Newton. So 450 Newton. So we have make sure that.
it will be very close to that, and you should have some
So,
factor of safety there, right?
so so actually, that was the rated, and you can see we can go up to max of 500 also in the specification we have mentioned. But the like if we cross the 450, the speed will go low. Like,
Actually it will be more than 450 from what I can see. So from the visual representation, I can see the distance between the point B and that line will be close to 50 That's 50, or let's say 60 Okay. If I calculate the on actuator force based on that distance, it will be 60, mm, that will be around 1000 newtons, right?
yes, sir. No, sir.
So that will violate your rating for the actuator.
No, sir. Actually, in the CAD design, sorry to interrupt, but the system is the CAD design is not in my system. But what we have calculated, we are not getting approximately of 450 newton. We were about
Yeah.
250
So that's
approx.
what I'm saying. I'm not able to understand how you got from T max to on actuator force. I think that I'm not able to understand how you reached that force value.
So let me show you the complete document where we have calculated everything.
Yeah.
So this was the calculation.
Yeah. So you calculated the torque value. That is correct. Torque value is correct. That's fine. So from reaching from torque value to the force value, that's the calculation I'm looking for.
So this is the
Yeah, you can scroll down.
actually, sir, sorry to say, but we have not mentioned it. But as we calculated, it was going up. It was in the limit of 4.
Okay, because I highly doubt that the calculation.
Uh, so, Anshuman, can you show me the CAD design where we can get the needs from? So Anshuman will be showing you the CAD design. With the can we can calculate it out. Right.
Yeah. In the meantime, if anyone has any other question, you can take that up. Yeah. I think that's the only doubt for me. Rest, I'm okay with the rest.
Any questions?
Mm. Are you showing the CAD design, or we can move to the next team?
Yeah, I think we can move on to the next team. It might take
Okay,
some
fine,
time.
cool.
If they want, they can present it at
Okay, sir.
the last.
Just give me some
As
5 minutes. After next team, we will show you any calculation.
Okay, so team number second. This is the last team. Uh, you can, yeah, you can raise your hand. I guess everyone is present on the screen.
Yep, I guess.
Okay, you can start the presentation.
Yeah, I'll just share my screen. I hope my screen is visible.
Yeah, it is visible.
Yeah.
Yes, it's visible.
Okay. So, hello
Around.
everyone. We are Team 2 and we'll be presenting our work on the topic of powered bonnet for electric vehicles. The task was to automate the bonnet of a electric vehicle to open and close with just push of a single button. So here's a list of topics that we'll be covering in the next few minutes. We'll be starting from the mechanical design and going all the way till the bill of materials. So let's get started. So the most important question here is how are we planning to drive the bonnet? And for that, we have some possible actuation solutions. The first one being planting a motor directly at the hinge of the bonnet or somewhere else and using a mechanism to apply the required torque. The second could be to use electric linear actuators and apply a force to generate the moment. And third could be to use pneumatic actuators working just like electric linear actuators but based on the principle of compressed air pressure. So after analyzing these three actuation solutions, we figured out that we'll be taking electric linear actuators owing mostly to the high precision that we want because the problem statement requires 1 degree strict tolerance in the position of the bonnet. So this is a visual representation of how the system would look to better understand the forthcoming details of the project. So once we decided that we are going to be using electric linear actuators, we went into the numbers and
A very natural approach would be to use two linear actuators on either side of the bonnet, but we figured out that that is just too much resource at work. So we boiled down to using one linear electric actuator and one hydraulic lift to support on the other side. Once we were done with the configuration, we came to finalizing the orientation, and to maximize the force output, moment output from the force, we would want to obviously keep the point of application as far as away from the hinge, and at the same time to decrease the extension ratio, we have kept the other fixed point of the linear actuator vertically below the hinge of the bonnet.
Okay, so now moving on to the governing equations for the plant, as shown by Bishop, the FBD, there are two major forces, the gravitational force and the actuator force F, and a simple torque balance across the hinge gives us the governing equation of the plant, whose implementation in Simulink can be seen. Next slide. Yeah, next is choosing the controller. So we started off with a plain vanilla simple PID controller, but when we started to play with the gain values, what we noticed that the curve of, no matter what we do, the curves of omega versus time were very sharp and had very steep gradient. So here's where we have made a very novel design choice in controller. We have implemented a alpha term which penalizes large values of alpha, the theta dot dot term in the feedback that you can see. And when we implemented this worked as expected, and the omega curve now you can see was quite smooth. And this controller's implementation in Simulink can be seen. Next slide. Now, after we had done the simulation, we got that we needed a maximum extension rate of 124 per second and a peak load of 450 Newton. So, based on some market survey research, we found a company named Linac whose actuator LA36 met all those specifications. So, we went ahead with that. Next slide. And as we had discussed in our approach, we are using one powered linear actuator and one hydraulic actuator. And to make sure that this design choice doesn't compromise the like static structural integrity of our bonnet, we did some simulations in ANSYS, and the results showed that we had a safety factor of 10, and the deflection was limited to 1 centimeter over the entire meter length of the bonnet. Next slide. Yeah, so next, some we needed some important relationships and the relationship between some important angles, specifically theta and alpha, whose definition can be seen. So we used a motion analysis software, Adams, to get this relation, and as you can see, it is quite a linear. Linear fit is quite good, represents theta and alpha relationship. Next slide. Now moving on to the practical stuff, tuning. So first part, so to make sure that the theta curve starts with a zero slope at both the angular extreme, we balanced torque, and this gave us the initial value of Kp. Then we made some reasonable guesses for other gain values, and then we tuned them to get our desired theta versus time curve, and also make sure that the omega and time curve alpha curves didn't have steep gradients, they were smooth everywhere. And then we iterated over this process to arrive at the final gain values. Next slide. Coming on to gain scheduling, we have implemented it in mass range and in time range. So what gain scheduling in time is that we have two independent set of gain values for the upstroke, the when the bonnet is going up, and for the downstroke. So by doing this, we can independently tune their parameters and hence get optimal performance in both the strokes. And we have implemented gain scheduling in mass range to make sure that the tolerance of plus minus 1 degree is met for entire 9 to 14 mass range that was given in the PS. And what we note, very good observation, is that the all the KPKD, all the gain values barely change much for the entire mass range. So this proves that our model is quite robust to change in mass of bonnet. Next slide. So yeah, this is the final model. Everything has been explained. The actuator is the only remaining thing, and that model we got through the data sheet of Linac LA36 actuator. They are given this relationship, and the final closed loop control equation can also be seen. Next slide. Coming on to some important plots, the theta versus time plot, as you can see, is very smooth. There has no sudden changes and is within the tolerance band at both 48 and minus 12 degrees. And the average power consumption, as you can see, is 250 watt over 11 second cycle, which translates to about 7.64 into 10 power minus 4 kilowatt hour of energy consumption. And to compare these numbers in the industry, JLR has an electric EV I-Pace whose battery pack is rated at 90 kilowatt hour. So our energy consumption is quite lower than that. So that's a plus point. Now I'll hand over to Vishak to wrap things up.
Yeah. So once we have finalized the mechanical design and the controller design, we moved on to the small details of the system, and we performed ANSYS simulations on the joints that we'll be using to connect the actuator to the bonnet. And we figured out that the maximum stress was 7.32 megapascals, which is very well within the yield stress of the chosen material aluminium. And we have a safety factor of about 25 to 30 for the same. So yeah, back to the most appealing thing over here, the CAD model. So this diagram shows very clearly how the positioning and the orientation of a linear actuator is with respect to the bonnet, and it is very well constrained into the white space. We have an animation here to show the working of the system. It opens in the first 4 seconds, holds up for the 3 seconds, and closes in the next 4 seconds, exactly as directed in the problem statement. Here we have the different views of the CAD model to show the positioning, the very less space that we're using, less than 20% of the allocated space. And next up, we have the electronic circuit where you can see the connection between different feedback sensors, the controller, and the linear actuator, and how they are going to be integrated together to work as a system. Finally, something that worries the companies the most, the bill of materials. So yeah, we have the major cost of our system is governed by the cost of the linear actuator, which is 87.5% of the total cost. Rest of the things take up the small chunks like the sensors, the mechanical parts, and the labor and the fitting charges. The total is going nearly 38,000 rupees. So, to conclude, we'd like to say that all the requirements were successfully met according to the problem statement, and we have come up with a very simple design with only two moving parts present. And we have focused maximum on getting a very smooth operation with no jerks anywhere and satisfying the tolerance limits. We have very low power consumption, which is less than half percent of the energy that is available in an electric vehicle, and even in a regular vehicle the energy is very less compared to what is stored in its battery. Next, we have very low space consumption. We can give nearly 98% of the total boot space as a usable space to the user. We are cost effective for such high end linear actuators. And lastly, we have a very long lasting solution which can work for more than 50 years, as our actuator can go for 1 lakh cycles, and it is very robust to chemical or other corrosive changes in the environment. So that's all we have from our side. Thank you very much.
Okay, thanks, team. Since we are on this right, just a quick question. So, what typical life cycle of vehicle is usually 10 years, right?
Yeah.
That's the standard. So, why do you choose a 50-year life cycle for this?
So this
Isn't
is
that a bit
something
too much over designing?
exactly. So this is not something we were targeting, but it's a byproduct. And see, we have chosen a very high-end linear actuator because we wanted to keep it inside the Indian market. And this is an industrial grade linear actuator, so it has been tested for 1 lakh cycles. So I mean that's just a byproduct that was not targeted to be achieved.
Okay, but you could have chosen a maybe a not so robust linear actuator with a
Yeah, we
lower
can
cost, right?
obviously go for that,
So,
but covering
because
the
cost
major
is
concern. Yeah.
yeah, please go on.
So the major concern for us was the extension rate, which is the 124 mm per second that we were getting according to our orientation, and the load. So getting that high speed and the high load, that made us push the limits of the actuator.
Okay.
And also we were searching for actuators that were readily available in the Indian market. So we didn't want any custom made things, but because we focus on scalability and all that. So
And we did find actuators that are like 25% of the cost, but they are not at all reliable. I mean, they can fail halfway through the run. So
What's the
not a good
reliability for them?
choice.
Have you
Yeah.
checked the reliability for them?
I mean,
Reliability
they
number?
had no warranty, nothing written on their website, or, I mean, not good reviews to say. And here we have directly contacted to the vendor in Chennai. and he has I mean he has shown the assurance that this would be working well, and they
Hmm.
have I mean they have a warranty period also.
Yeah, that's fine. Means for the other manufacturers as well, they all have their data sheets with these numbers. So
Yeah,
did you go through that?
yeah, we went through 3 4 data sheets, but I mean life cycle is not something that was really mentioned in many of the I mean I'm not very sure if I saw that anywhere.
Okay.
I mean,
Okay.
this company is a global leader, so they have a very well maintained data sheet. So, I mean,
Okay.
literally some of the parameters were mentioned which are not usually used.
Okay. One more question. If you can go to the mechanism, the CAD part of that.
This one?
Yeah, yeah, that's good. So your what the part where your linear actuator is connected to the frame, the bottom part.
Yeah.
Yeah, yeah. Where you no, the where you had your
Okay.
pointer
Yeah.
previously.
Yeah.
Yeah. So that part must be rotating, right?
Yeah.
So you mentioned the stress analysis. That's why I'm saying.
Yeah. Yeah.
So have you done any analysis for that part as well? Because you mentioned the
Um,
stress analysis for the top part, which is okay, but I think the bottom part might be more critical one.
Yeah, so we did perform analysis for that, and the stress value was less than the top one because that is under acceleration, and the direction is also changing. I mean, the direction is also changing for the bottom part, but not at the high rate. And we did perform the analysis for the bottom one. So for the top one, as I said, it's 7.32, but for the bottom, it was nearly 4.5, I guess. And the location of that point, I mean, is it connected to the horizontal plane or the vertical plane? Depends mostly upon which exact vehicle are we going to uh, fit this mechanism.
Okay, understood. And what about the yeah, I think that will be covered in that. Yeah, bearings. You must be using some bearings around that,
Yeah.
right? Whatever. Okay, fine.
Any more questions?
Yeah, a similar question, like the same question that I asked earlier. Just wanted to get an idea of what strategy you use. So, other than simplicity, what are the other parameters you use to basically arrive at the decision of using simple linear actuators rather than any sort of mechanism?
Yes, sir. So, as you said very correctly, that simplicity was our first target. We did not want to involve many moving parts or custom made mechanism because the number of parts you increase, the points of failure would increase. But at the same time, our major focus was to fulfill the requirement of the problem statement, which is to get a extremely smooth graph between theta, which is the position of the bonnet, and time. And at the same time, I mean the time, like 4 seconds for opening, 3 seconds hold, and then 4 seconds to coming back. So getting that exact equation, getting fitting into that model of 11 second cycle, and no jerks and a very smooth operation, that was the major target. So that's why we had to, as I said, get high speed at the same time, get high load and very high sensitivity, so that we can fit this actuator in a closed loop feedback system.
So just wanted to add that it was clearly mentioned in the PS that control strategy is not needed. So you could have used that time in maybe innovating or optimizing your current design. I mean, this is an innovative solution. I like it using different actuators on different ends. But just wanted to mention that since your target was to satisfy the PS, you could have done some innovation by not spending a lot of time on the control strategy.
Sure, sir. I'll take that as a feedback.
Yep.
One more thing. So, do you have any, let's say, there's any failure mitigation strategy for the same? So, for some reason, let's say your linear actuator is not has failed, and you're not able to move it anymore. So, will the user be able to open and close the bonnet in that case?
Yeah, I mean it's connected with pin like kind of pin joints with the bonnet and as with the chassis. So you can remove two pins and get the entire mechanism out and use it as a regular bonnet till the time you find a replacement or get the linear actuator repaired by the company.
Okay, that is still a lot of hassle for the user, right?
Uh,
Removing that joints, and if it is getting removed that easily, then I highly doubt uh, the steadiness for that joint.
Like our like structural simulations showed quite good safety factors, and
So in
the
that case,
actuator was also rated for 50 plus years. So we doubt
yeah,
it would fail.
so your structural simulation only shows the static analysis, right? So you
Yeah.
don't have
mm,
any durability. So if you are considering NVH, so if it is getting removed, there will be some tolerances in between. There will be some NVH issues because of that, right? If you are able to remove that pin joint somehow in whatever manner, it comes with some disadvantages as well.
yeah, that could be worked out in dynamic simulations, I guess.
Okay, yeah, that's all from my side.
Team 16, do you want to present that CAD model? If so, then you can raise your hand. Fine.
Are we done with all the questions? So shall I stop presenting?
Yes, I think. Great
Thank
topic.
you.
Yeah, thank you very
Thanks a lot.
much.
Thank you.
Uh, Team 16, now you can share your screen.
Yes, sure, sir. As we were discussing about the distance between the range points, let me first
Yeah.
share my slides. Good, yes. I'm sure that my screen would be visible to you.
Yeah, it is visible.
Yes, so I think we have missed the point that here only we have described the distance between the bonnet and the hinge. That is the two hinge points. That is the actuator and the bonnet hinge
Okay.
point. That is about 150 millimeter.
Okay,
Uh,
that's 180 mm, right?
so
So if
you
you
were
go
right,
back to
sir.
your,
There are some miscalculations. You were right, sir. So
so
previously it was F max was 137.66 Newton. So
yeah,
after correcting it, we got optimized value of F max is equals to 348.84 Newton.
yeah, and that is it directly perpendicular to the bonnet? The connection of your actuator is perpendicular to your bonnet, or is it at some angle? If it is at some angle, that angle will also again further increase your
Okay.
force required
Angle between bonnet and the
Yeah, I
actuator.
believe.
actuator.
Yeah,
So
so actually it would be transient sort of a thing. Sorry to interrupt. It would be a transient sort of a thing. So yeah, like as the Panshu just mentioned, the like the distance will not be 180 based on the angle, based on the opening position it is on. The value would change actually.
Yeah, the angle
Yes,
value will
the
change.
actually the calculation is done at the minimum when the angle is zero, like when the bonnet is in the closed position. So considering that was the maximum, as the bonnet will raise, it will eventually load will decrease.
You can't say that that's the worst case situation, right? You'll have to check at other angles as well. There might be some angle at which, since the angle between the bonnet and the actuator is changing, so there's a possibility that although the overall force is low, but since the angle is higher, the effective normal force that we are getting on the actuator will be higher. So you need to check that as well, right?
so we will just optimize our equations as it would appear that there must be some miscalculations.
Yeah, I understand. It's okay. Thanks for thanks for the clarification. Yeah.
Thank you, sir. Thank you, sir.
Thank you, sir.
So we have completed all the presentations. So this is all for today. I want to thank all the panelists for giving their time, and I want to also thank all the participants for actively participating in Inter IT Tech Meet 10.0. So now the meeting ends, and you all can leave. Thank you, and have a nice day. Just wait a minute. There's a participant who has a doubt. Just wait a minute. Yes, Laksh.
Hello, yeah. If you guys allow, I had something to clarify from the judges. Like, can I do it? We are
Yep,
team
sure, you
two.
can
We just
ask.
had a presentation.
Yeah, yeah,
Yeah,
sure.
so I think according to the PS, it was mentioned that we need a strict tolerance band of plus minus 1 degree, and the rise time and the hold time and the settling time also mentioned. That's why we had extensive controller design and gain scheduling mentioned. So,
Yeah, okay, yes, your point is correct, and uh, but there was also another point that I mentioned in the PS that the way you control the bonnet is not needed. So the times were given, and this is something I also clarified in the Q&A session, that the times were given just for a reference, so such that everyone can follow a single sort of a cycle, so that like if I don't mention the times, then it would be difficult for us to judge when, because someone might come up with a solution where their holding is also consuming power. So that is why I gave a proper a time for the holding and all of that. There is a sentence in the PS. I specifically added that because again I didn't want everyone to uh, do the smoothing and everything which you guys did. Like for you guys, like you had done a good job with the mechanism,
yeah,
but yeah, you also gave an extra effort into the control strategy. So that is something that I just wanted to mention, that uh, yeah, you could have given that time in innovating something else. That's it. Like it's not a problem, don't worry. Like
okay,
I mean the mechanism matters, and your plots are correct, so don't worry, like you will get proper marks for that, so it's not a problem.
that clarifies it. Thank you so much.
Yes, yes.
Uh, okay, so now we can end the session. Do anyone have any other doubts? I guess there's no other doubts. So, okay, have a nice day. Everyone can leave.
Thanks a lot everyone for joining. The solutions were really great, had a great time going through them. Thanks a lot.
Thank you, everyone. Thank you,
Yeah.
Dipanshu, for
Thanks, everyone.
thank you. Thanks, everyone. Thanks, Inter IT team. Great event.
Thank you, everyone. Bye.
Have a good day. Bye.
Yeah, yes, sir, you were asking something?
No, 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 I was just saying, have a good day, right? Bye.
Okay, thank you, sir. Bye, sir.
Thank you.
Bye. Bye.
Bye.